1-hour session together. This is I'm Mark Richardson speaking from Vibrant Technology in Centennial, Colorado. As you can see on your screen, today we're going to talk about detection and diagnosis of 3 common rotating machinery faults. So most of the presentation is going to be about ME-scope and how we use ME-scope in a remote monitoring situation or for remote or portable troubleshooting, or simply as a post-processing software package for detecting and diagnosing machinery faults. So we're going to look at 3 different cases today. Let me go through a few slides with you. These are some slide presentations that I have presented at other conferences, Vibration Institute, and there's one coming up next month called IMVAC, I-M-V-A-C, which stands for International Machine Vibration Analysis Conference. I certainly invite you to come. We're going to do demonstrations and consider more of the details of these vibration problems. You can see on this slide here there's a few slides here. One is that for decades vibration measurements have been used to assess the health of rotating machinery and structures. Vibration waveforms carry telltale signs of mechanical changes in a machine or structure. And 3 of the most common health problems are unbalance of rotating parts in a rotating machine, misalignment of rotating parts, and what's called SoftFoot or loose mounts or a overly compliant foundation. So when machinery gets installed out in the field, in a process plant, there can be literally thousands of rotating machines, and most organizations, whether they be power plants or petrochemical plants, oil refineries, whatever, have ongoing walk-around data collection and in many cases online monitoring systems for detecting these mechanical failures. Here's a slide that I found on the internet kind of showing how frequency spectrum analysis is used along with enveloping. And you can see some different cases here on balance. That might be called the first order or the running speed of the machine. The peak at that frequency grows outside of its envelope, and so that's a way of detecting unbalance. Here's some rubbing of maybe bearing seals, bearing instability. That's a fancy word for saying there's something wrong with a rolling bearing or even a fluid bearing. Here's some misalignment of rotating parts and some aerodynamic resonance. So that might happen in a pumping system where there's some fluids and there's some instabilities. So many different mechanical problems can be detected by looking at spectrum data. Here's another graphic of what are provided with roller bearings. Most of the rolling element bearings, roller bearings, ball bearings now have data associated with them, so that at the various orders of a machine, the running speed of the machine, you can envelope the spectra and detect bearing problems that way. So here's another, next slide is about operating deflection shapes, which we can look at in animation with ME-scope, but we can also process that data and in ME-scope with our scripting now we can track the running speed, we can pull off peaks in bands or at different frequencies and store those into a shape table. And in that case, we would call it an operating deflection shape. We're not measuring the internal forces. The ODS, the vibration, is self-excited by the internal forces. So we can simply measure vibration on the surface. So you can see here in this graphic, we're going to look at this machine a little later. This is one of our rotor kits that we have here at Vibrant. You can see the little blue cubes. Those are indications of tracks or accelerometers that we place on the running machine, and then we measure its ODS with the acceleration X, Y, and Z motion at various points on the motor and bearings and on the base plate. We can talk about ODSs of three different kinds: time-based ODS, frequency-based ODS, or order-based ODS, which again would be a special case of a frequency-based ODS. But we can look anywhere in a spectrum, and especially if we've got some resonant assisted vibration, in other words, resonances are getting excited, which is usually always the case. We can detect, we can measure ODS data from that. Changes in the ODS. So we're going to talk about metrics here. Now you can see one up here on the screen, and we're going to get into this in more detail. We have two different metrics for measuring changes in an ODS, and in this case we're going to look at order-based ODS. In other words, we're going to pick off the frequencies at the running speed or multiples of the running speed, and we're going to start out with a hypothesis. Can we detect unbalance, misalignment, and SoftFoot through some measure of unique changes in the order-based ODS? So if the answer to that is yes, that the ODS does change with these different mechanical faults, how do we measure a significant change? We can envelope the spectrum. That's one way to do it, but we need somebody to tell us how to set up the envelope. What if we simply want to measure changes in the ODS? Do we have a metric for doing that? In ME-scope, we have two different measures, one called the modal assurance criterion. Now, this has come out of the modal analysis community. It measures the collinearity between two shapes. So if I have a baseline ODS and I have, let's say, a current ODS that I'm measuring with an online system or a portable system, walk-around system, MAC would be one way to measure the difference. The other one we call a shape difference. And here you can see a bar chart, and we're going to look at these in a minute, where we are measuring the difference between these two ODSs. You can see from the picture that the machine is vibrating differently, and the little bit of an interruption with a cell phone, but anyway, in this case you can see graphically a difference, and both the shape difference indicator and the modal assurance criterion measure those shape differences. Now, one of the problems with the modal assurance criterion is it only measures collinearity, whereas shape difference measures the actual difference between the two shapes in terms of their exact values. So in a worst case, if I've got a mechanical fault in a machine, maybe the shape doesn't change, but its amplitude changes. In other words, the peaks get bigger. That's certainly an intuitive idea that we can apply to spectrum analysis. SDI, and we'll see some examples, is a more accurate way to measure the difference between two ODSs. All right, let me put this down, and we're going to go to ME-scope here, and we're going to look at this rotating machine. Now I can put a, this has also got a photo model, so there's a little more graphic picture of this, this rotor kit. Let me go over here to my project. This is a project I have open in MeScope, and we can provide all these projects to any of you that are attending that you can run in your copy of MeScope if you own it, and you can do many of these same things. Now, some of these options you may not own, so I'm going to go into one of the options here and show you what we're going to demonstrate here. Here is a block diagram of a layout of MeScope with one of its options called a console, and in this case we used to refer to it as Mechanicom. Now it's simply some options to MeScope. Here's some portable boxes that have MeScope running in them in a solid state computer. A database that can be either in the box itself or in the cloud, and then up here the console software, which can run on many different devices, showing graphically the data that's been logged into this archival database. So that is what we're going to show here today. Let me look at some of these other, oh boy, can't show those. Let me go and see if I can find them and show them to you. They haven't been linked up to this particular copy of MeScope, so it's telling me that it can't find them because each of these has a path. You can see that the path for each of these added files is not where that file exists, because I copied it into a different location. Up here, if I put my cursor on the project itself, you can see where it's actually located on my disk. It's in the MeScope unbalanced facts. So I can go there and locate those added files, and then I'd have to reattach them to this project. So let's just go there for a minute and look at some of those graphics. I'm going to use my Windows Explorer and go to my documents, MeScope, unbalanced cases, should be down here somewhere, unbalanced facts. Okay, so here are those same, and I just wanted to show you some of these JPEGs. So here's a picture of the machine that we took the data off of. You can see some accelerometers on the base plate, some of them on the bearing blocks, and one over here on the motor. Let's just take a different look. There's a clearer picture. Here's a different angle showing some of the accels, and then here's a diagram showing how we simulated unbalance on this machine. We put weights on the inboard and outboard rotors. Now the way we're going to diagnose this is using ODS data archived into a database. That's where we've identified these unbalanced cases, and then when MeScope archives new data into the database, we're going to use something called facts, which is really a term that we created. It's called fault correlation tools, where we're going to correlate ODSs in the database with data that's been recently archived into the database. So let me put this down then, and I think we've looked at all the pictures. There's a tech paper that we have on our website that explains a lot of this and how we actually measure the difference using the SDI metric between two ODSs. Let me start this. I've got a number of hotkeys up here. and I'll just move the cursor along. You can see the hotkeys. This is a standard feature now in ME Scope. And I got one over here called Start Over. So I like to create a hotkey that says Start Over. Here's one that's going to archive, turn on the archive to the database. And I've got first order and second order ODS data here. So this data has all been pre-recorded in ME Scope. Actually got a third order. So what we've done is simply pick off the peaks in the spectrum data for first, second, third orders and stored them in this copy of ME Scope. And then we're going to use these hotkeys to look at the data. So here's a case of, I press this Start Over. You can see this is the first order. This is the running speed of the machine, 2,000 RPM in both cases, so it's balanced. And I'm just comparing, this is a comparison display, balanced with balance. So it's simply comparing the ODS with itself. You can see the MAC value between these two ODSs is 100%. In other words, it's the same ODS. And the SDI value is 100%. Both of these metrics range between 0 and 1. You can see on the model the blue cubes are where the data was actually taken, or in this case the data that we've saved in ME Scope here. So we've got a couple of uni-axes. These little cylinders are uni-axial accels and the cubes are triaxial. So we got a combination of different data here. Triaxial on the bearing blocks and triaxial on the motor, and then some, here's a triaxial down here and a couple of uniaxials on the base plate. I'm going to turn off the photos on the surface, and whenever we have a photo model like this in ME Scope, we can always, there's always a surface underneath. So if I click on this button here, it shows me the photographs on the surface. If I click on this one, that's just the surfaces themselves. A little bit better sometimes for looking at engineering data. Now I'm going to click on this next one, a small inboard. And we won't go into the programming because I want to go ahead and show you in the console how we can detect these various changes. But you can see over here, the one on the right now is animating with a little more motion. That's a small inboard weight. And so a small inboard weight on the inboard rotor is causing a change in the ODS. The MAC value dropped to 82%, so that's, you know, in the questionable range. The SDI value dropped considerably, saying this is quite a different shape. Let me just try one more here. Again, the MAC value is staying at 83. You can see the animation is increased here because this one is scaled relative to the left side. And the SDI values drop down considerably. So small outboard, a worst vibration case. Let's go to the worst case here. Both unbalanced weights at 0. These are large weights at 0 degrees. And so you can see the loose end here of this thing is really moving around. The MAC value didn't change a whole lot, but the SDI value is a good discriminator of the difference in these two shapes. Okay, so let's go and drag these over here, and now I'm going to show you how we can diagnose the difference, or let's say diagnose the machine fault by looking at these differences. So here I'm bringing up our console software. I want to go back to the machine gallery, and I've got a bunch of machines in my database. Let me make this large so you can see everything. So these are all different machines. So the database, the archival database is machine-based, and I can keep a large amount of data, terabytes of data in that database. that are logged in there from Emiscope, running in a yellow box or just post-processing data, and then I can go in there and compare data that's been archived with data that's coming in from Emiscope. So I'm going to open up this one called Big Rotor, and you can see a bar chart that's showing up. Big Rotor has a number of panels associated with it. I have a trend plot here. Let's see if I can put the trend plot up. Here's a trend plot. So here's some data that's coming in. Not very interesting. Let's go back to the facts plot. Now facts, as I said, is SDI values between data that's been already archived in the database and identified, and data that Emiscope is going to archive into the database when I remotely tell it to do that. So I can set Emiscope up to either continuously archive data, or let me put this down. Now I need to come back over here and start the archiving. So right here I'm going to press this hotkey and it says archive in database. So I've triggered the archiving process from Emiscope. And you can see over here in console I have this key. So for this machine, for this particular machine, it's simply archived in the first order case number 6, which is the one we were looking at over here last. And I can go back and press a hotkey. But now if I go down here to this facts bar, these are the 10 highest values of SDI that already logged into the database that correlated with the data that just came in from Emiscope. And you can see that if I put my cursor on here, it's identified this one. It's got a value of 1. In other words, it's complete. It's 100% identified first order case number 6. Now the next closest was down here, first order case number 5, and it's only 73% like the case number 6, the large unbalance. There's case number 7. So 5 and 7 are close, but those are different unbalanced cases that are not diagnosed, and then you can go on down the list here. And so some of these cases down here are clearly not diagnosed as that particular fault. So I'm going to come up here and push some of these keys. Let's push the, we're on first order. Let's go back and push the balance case. So you can see that Emiscope remotely has put the balance case in, and facts over here is saying from the data that's already been archived, I've recognized that as the first order case number 1, which is the balance case up here. So if I push case number 2, a small imbalance, the console software is going through the database and telling Emiscope to archive that case. And here it is. And so facts down here now has said that's case number 2. It's similar to, if I put the mouse here, case number 3, which it's 80% like case number 3. So let's just go see what case number 3, that should correlate perfectly with data that's already in the database. And you can see that case number 3 there, pulled it out, but it's very close to case number 8. So 96%. You can see what's going on here, that case is going to be difficult to diagnose compared to case number 8. It's they're 96% alike. And here's case number 4, case number 2 at 80%. let's just try another case. Let's go case number 4 and see how FACS can pull out its ODS. Okay, well that's a pretty clean case there, and you can see it's 80% like case 8, case 7, case 3, and so forth. So anything over 90% is a pretty clear indicator, and of course FACS is simply order everything that's in the database so that I can decide by looking at this data whether I can diagnose a condition in the operating machine. Let's go to the second order and see whether the results are a little different. Obviously they will be. There we have the second order, and case number 1, it went back to case 1, and that's clearly not like any of the other cases in the database for second order. Let's go out here to the extreme case, unbalanced, 0 degrees on both rotors. You can see the second order here is really moving around, and FACS has pulled it out, and there is nothing like it in the database. Let's go to the third order. Now this little message coming up here is a message that MeScope sends to console. This is another way that when MeScope is doing stuff remotely, it can put this message out to the console operator, which it can go through a cloud database or any type of a remote database on a network. The database is the archival database is network based, and all this software is network based. But you can see it's clearly pulling out. There's a third case, case number 1. Let's go look at some of here's the most extreme vibration case using the third order. Boy, look at it moving around over here. You can see quite a difference. Console over here has pulled it out of the data by comparing that ODS, third order ODS, case number 6, with the data it has saved in its database. Okay, let's leave this alone, and I'm going to come over here to MeScope and close this project. And it says, do you want to save? I'll say no. Let's open up another case here that's a little different, and this is misalignment. I'm going to open up this project, and this is a different machine. I have a start over. Let me hit my start over. Here you can see it going through some scripting, and here's a similar machine. We can look at the photo model. It's kind of a crude photo model, but you can see a very complicated machine. It's got a lot more accelerometers mounted on it. You can see them on the bearing blocks, on the base plate, and one on the motor. Let's go back to the solid model. It just looks a little cleaner, a little easier to see things. Okay, so here we are, 2000. This machine is running at 2000, and let me look at the hotkeys. Okay, I've got first order, second order, and then 3 different cases here. The machine is aligned. It's misaligned with what we call parallel misalignment. Now that is simply the driven part of the machine, the shaft with the rotors, is misaligned with the motor in a parallel sense. And then we have angular misalignment, which is the shaft with the rotors is at an angle to the shaft of the motor. If I go back to the photo model here, you can see how we did that. There's a couple of little screws here that actually move the bearing blocks and some of the framework underneath the bearing blocks, so that we can crank in with these little screws here, both parallel misalignment and angular misalignment. So that was done, and then data was taken, and we have that data recorded here in MEScope as a set of ODSs. Let me just push one of these hotkeys here. Here's a parallel misalignment. Okay, you can see both MAC and SDI dropped considerably, saying that the one on the left, which is still the aligned shape, is quite different than the comparison shape over here, which is down here in the shape table, parallel misalignment. So even though the pictures don't look a whole lot different, the metrics are telling us that these two ODSs are quite different. Now we're going to go over here and look at angular misalignment. SDI really dropped. MAC value not so much, but again, quite a difference in the ODS data. All right, well, let's remotely look at this data from the console side of the database. So I'm going to come over here and go back to the machine gallery, and this particular machine is called misalignment. Here it is right here, misalignment offline. So let me click on that, and here's another bar chart with a fax bar chart for this machine. And oh, I haven't, you can see all the hotkeys are dimmed out for this machine because I haven't started the archiving over here in MEScope yet. So I need to come way over here in the corner, and let me just click in here, and you can see it says archive. Let me make that a little larger so we can see it. Here it is, archive data. So that's going to connect MEScope up to the database, and now it's going to archive data into the database. You can see these hotkeys lit up. So on the other side of the database, the console software is live, and I can remotely tell MEScope what to do from here. So let me push the aligned button here, and so MEScope now is aligned. And over here, the fax bars, I've got 3 fax bars now. See, this one is for all my degrees of freedom. So that means all of the accelerometers on the rotating machine. This bar here is for, let me get this so you can read it a little better, simply the motor and bearings. So we can maybe get this around a little better to, there it is right there. Now you can read motor and bearings. So what fax is doing is simply taking the motor and bearings data from the ODS that was logged into the database from MEScope. And then down here, this bar is only going to use the base plate data. So what are we seeing here when we put the cursor up on these bars? First order, all DOFs aligned. The second bar is also detecting the same result, but it's only using the motor and bearings data. And then the third one is also detecting aligned, although it's got another one right here. See, this is saying that just using the base plate data, I can't tell the difference between the aligned case and the misaligned case, parallel misalignment. So that's saying that the base plate data is not sufficient. Now, how did we set these bars up in the console? Let me just define bars. Here it is right here where these bars are defined. We're using event storage, which is the events that I've identified, the various ones, and I'm going to go in here and edit the bar. So here is the data that's coming in from MEScope. This is ODS data. All the degrees of freedom are turned on here. And you can see they're numbered differently, and there's 1, 2, 3, 4, 5. We could go back to Emiscope and find out where those points are, but these are all the accelerometers. Now if I open this one, you can see that this is the motor and bearings. So motor and bearings are numbered with these numbers, 100 up to 108, and then the other base plate is 1 through 5. So those are the portions of the ODS data that I can track with the fax bars over here. So you can see that I can track any part of the ODS data being logged in from the machine. This could be from walk around data collection. This could be from an online system using the Emiscope running in a box somewhere, or simply Emiscope post-processing data from some other hardware. Let me push the parallel misalignment and we'll see what's going on here. Okay, you can see over here we're still running at the operating speed, and the MAC and the SDI have dropped considerably. Fax over here is saying that it's parallel misaligned. When I use all the data, it's parallel misaligned if I use just motor and bearings data. So this is showing that motor and bearings is enough data to detect this misalignment problem. However, if I use the base plate, it detects it with 100%, but it also, this is kind of the reverse of the case we saw before, where it can't tell the difference from the base plate data between the misaligned case and the aligned case. Let's try angular misalignment. Okay, here it is. Well, now we got a clear indicator, angular misalignment on that bar, angular misalignment on motor and bearings. And even though it's saying all DOFs, that's the case that I logged in as an event. I said all the DOFs, and Emiscope's logging all the DOFs, but these fax bars are only using a portion of it. So you can see here that this, it wouldn't matter whether I use base plate, motor and bearings, or all the data, I clearly can detect angular misalignment. And these are the next best cases down here that are very low SDI values. That this is just SDI, not the MAC, but it's a clear indication of a difference in those ODSs. Okay, that's first order. You can see it's all first order. Now let's go to second order and see if we can pick up these changes as easily. Okay, so here's Emiscope over here, and wow, look at second order. Second order is a very strong indicator of alignment, alignment, and alignment. So it doesn't matter which data I use. Here's the next worst case right here, misaligned, but it's only 66% using the motor and bearings. And over here, similar, using all the data, it's 61%. You can see here, here's some bars on the third one. This is 52%, just using the base plate data. Okay, so let's back and try the parallel misalignment using the second order data. So you can see, rather than just enveloping, we can envelope too, and we can alarm if an envelope is exceeded at in a certain frequency band. But here we're simply picking off peak values at the second order, twice the running speed. And all three of these bars are showing a clear indication. Here's, well, we're down here at 66%. Again, not a very strong, I mean, this is a very strong diagnosis of parallel. Let's look at angular using the second order. So you see, I can set this stuff up a lot of different ways, And again, second order is a stronger indicator. I could actually be logging second order data all the time, as well as first order data, into the database and set up bars that look at one or the other or both. Okay, we looked at unbalance, we looked at misalignment using the fax bars and archive data. The last thing I want to look at is what we call SoftFoot. And the way we did that was simply to run one of these rotor kits at some different speeds. And the rotor kit is sitting on rubber mounts. So as we run at different speeds, it's almost like a mass on a spring. The ODS is going to change drastically. So let's, let me close this, and we'll make this large again, and I'm going to close this project, and we'll say no, we don't want to save it, and we're going to open up one called the VTech SoftFoot. And we won't use the fax bars in this case. We'll just look at the difference between the ODS values measured by MAC and SDI. Fax is really simply the SDI metric, but using a database. So here I'm going to, well, let's just start the animation and take a look here. Now, before I do that, let me show you some pictures. Here's one that's a little fuzzy. This is the real machine. You can see the accelerometers. These are triaxial accels. And we've taken two sets. We've done this with different sets of data. In this case, you can see we've got triaxial accelerometer here, here, here. A couple up on the bearing blocks, none on the motor. Let's see if we can look at, okay, so there's some more accels back here. And we're using a tachometer to measure the speed of the machine. That's different stuff. I don't know how those got in there. Let's just go back and take a look at one other thing, the SoftFoot. So here's what we're using this machine for. You can see the tachometer. So we simply varied the speed of the machine, and Emiscope can, using the tach signal, it can measure the machine just like it just finds the biggest peak in the tach signal spectrum, and that's the speed of the machine. And this machine's sitting on some rubber mounts, so as we change the speed of the machine, the ODS measured with these accelerometers is going to change. That's the whole idea. So let's just start the animation and look at some of this data. I'm going to do a comparison animation here. So here it is, and I've got 9 different speeds of the machine. These are called the SoftFoot shapes, and they're ODS data. Now you can see some pretty nice vibration going on here in terms of the smoothness of it, and we've only measured data at the accelerometer locations. So this is another feature in Emiscope, and we call it shape expansion. What we've done is taken the experimental data from the accelerometers. In this case, we've only got 5 of them on there, not even the 8. So 5 accelerometers you can measure with a 16-channel machine, analyzer or data acquisition machine, and then 1 channel for the tach signal. So 16 channels would be filled up with 5 of these accelerometers, and then we use something called shape expansion, and that is a curve fitting of the mode shapes of this machine to the operating data. So what we're saying here is that the ODS that we measured on the machine is actually a summation of contributions due to the modes, and so the animation is actually being driven by an expanded ODS. And let me show you the model. There is the model that we built in Emiscope using our FEA capability and our SDM capability to actually attach the bearing blocks to the base plate. And now what we're looking at is the expanded ODS from the 5 accelerometers, expanded with a curve fit of the mode shapes. Let me stop this and we'll actually look at the mode shapes. I think they're in this project. So FEA modes, let's see. Maybe not. I didn't include them in here. Oh well, let's just start the animation and see if we can look at the mode shapes here. So we're going to go to open up the FEA modes. Okay, so we got some mode shapes here, I believe. These are the mode shapes of the bearing block and base plate. And as I said, we used our FEA capability to build to get the modes of one bearing block, copy and pasted them to the other one, and mounted the bearing blocks to the base plate with very stiff springs. Let me get these up here. Put those down, and we'll hit the arrange for animation again. So here are the mode shapes. The first 6 modes are the rigid body modes of the base plate and bearing blocks in space. So with FEA, we simply start out and just model the motion of this thing in space. Very easy to do in Emiscope. Build a couple of small FEA models and then attach the models together, the modes together, using SDM. These are the tools we have in Emiscope for doing this sort of thing. Then, in order to animate the VTEC rotor model, we simply use our geometric interpolation. Now you can see it's quite exaggerated here, but this modal model is going to be the thing that we use, all these different mode shapes, and we used the first 10. Now if you use too many of them, then you're kind of curve fitting down into the details. It's like using too many polynomial terms to curve fit your FRF data. You don't want to use too many modes to curve fit the ODS data. But we did want to include the rigid body because the machine is primarily bouncing around as a rigid body in space on its rubber mounts, but there is a little bit of flex in it also. So let me just go back and we'll look at the different ODS data. But this is how we got this model to animate with shape expansion, using a modal model to animate our data. So I'm going to go back here and we're going to go back and animate our SoftFoot data, and I just want to look at all the different cases. Copy of SoftFoot. Okay, so here we go. We'll move that over and we'll do this. So I got the 2 shape tables back. Now these shape tables have almost 2,000 measurements in them. So even though we only measured 15 degrees of freedom, we expanded them with the mode shapes of the base plate and bearing blocks to 2,000 degrees of freedom. So that's how we're getting this thing to animate so nice and smoothly. And this is all standard in ME scope. All right, the first one is 1300, and down here we're comparing with 1300. So two shapes exactly the same. If I just walk along here in the comparison, this side, at 1400, you can see the ODS is starting to change drastically, and both the Mac and the SDI are detecting it. So the one on the left is the 1300, the one on the right is the 1400. Let me just click on down here, and you can see that as we increase the speed of this thing, this is simulating SoftFoot, the ODS is changing drastically according to these metrics up here. And you can see a little bit of flex in the structure. Even at 1300, there's a little bit of flex there, but a lot of rigid body motion. All right, down here at 2000, you can see that and we also put a little unbalanced weight on the outboard rotor to make this thing vibrate. You can see that it's vibrating quite a bit. The other thing to notice here is that these are complex. An ODS is a complex shape. So in order to curve fit, to get this to work right, we had to measure what's called a complex participation factor of each mode in the ODS. And then we use those complex numbers to expand the ODS, and we end up with a complex picture like this, which is very much realistic. Now down here we've got several cases of 2000 RPM. They were actually different data taken at different times. So let's change our baseline here to, let's say, 1900. So now when we're comparing 1992 to 2168, slightly different speeds, the ODS is, Mac says it's 93% the same, SDI says it's 89. So there we are, between those two speeds, we're already detecting some change in the ODS. Let me just go up here and, okay, there's 1900, they're both the same. There's 2000, 99% the same, both Mac and SDI say they are. Here's 89 and 91. So between well, you can see over here too, 1992 RPM as our baseline, and 2200 RPM, the SDI is starting to drop, and here we got it down to now at 22.7, a different measurement. 1992 here, 2227 here. We're starting to see a significant difference in the SDI. Let's go down here closer to 2000. Let's put that up, and you can see that those are significantly different, those two speeds. Let's go compare the two speeds at 2227. The RPM is the same. These are two different measurements made at essentially the same speed, and you can see that they're 94% alike. So this is kind of showing us the difference in experimental error from one measurement to the next. And again, there's the same shape, 100%, 2100, almost the same between 2100 and 2200. Different measurements, slightly different speed. Now as we drop the speed, our reference is the 2200 here, so we're starting to see some significant difference. Okay, I believe that wraps up our discussion for today. And Brian, do we have any questions from the audience? We forgot to solicit some questions. Did we have any come in through the email?
No, we didn't.
Okay. I apologize. We covered a lot of material today. We covered facts from the archival database and the console use. We've used that to detect and diagnose unbalance and misalignment. And we looked at using different acceleration data from the motor and bearings versus the base plate. And then in this case, we're simulating SoftFoot by simply comparing ODS data on this machine at different speeds. Now, normally the machine would not be running at different speeds, or it could be, but if we had this data archived into a database, then FACS would identify for us significant changes in the ODS. All right, next month we'll have another discussion. I thank you all for coming, and this is being recorded, so it will be out on our YouTube site in a day or so. Have a good day. So long.